Now, one of the more interesting questions we might deal with is to determine the final temperature a sample of substance would reach if we had a certain amount of reactant undergoing our chemical change. So here we have 60.60 grams of butane undergoing combustion, and the question is, to what final temperature would we be able to heat some aluminum? Well, just like before, we first identify our system and our surroundings. We can determine or write down our givens. So we have our given for our system, and we can even record how we would determine our enthalpy change for our system. It would be equal to moles times our molar enthalpy. Okay. We know that it's an exothermic reaction, so delta H is going to be equal to negative QT. We know it's exothermic for two reasons. One, it's a combustion reaction, and two, I have a negative delta H reaction. And finally, we can identify our amount of information or our givens for our surroundings. Now, when we do our surroundings, we have to still keep in mind our heating curve, because we're going to start heating it down here at 25 degrees Celsius. And the question is, where will we end? And so we might be able to heat it just to its melting point. We might only be able to melt some of it. We might be able to heat it to between its melting point and its boiling point. So the first step will be to determine the total energy that is present in our system, or that our system releases. And so now all we have to do is take our moles and multiply by our molar enthalpy, and it tells us how much energy our system releases. So now I know my system releases this much energy, and I know that delta H is equal to negative QT, so my total energy is equal to negative delta H, which is equal to, now that we know how much energy we have in total, we can now start looking at using it for our different regions of our heating curve. And so our first step will be to see how much energy is required to heat my 2 kilograms to its melting point. Okay, and so we know that energy in this region is calculated by Q is equal to MC delta T, where I have my temperature change from 25 to its melting point, and I find that it requires 1,104.5 kilojoules. So that's how much I need to get to its melting point. Well, I know that I have a total of almost 3,000 kilojoules, so the difference between these two would be the amount that I have left to potentially melt it, heat it after its melting point, boil it, and heat the vaporization. Okay, and so I can calculate how much energy is left after I bring it to its melting point. So this means that I have about 1,900 kilojoules to both melt it and heat it after that. So now my second step would then be to determine how much energy is required to melt it. Okay, and so I'll multiply my moles of aluminum by my latent heat of fusion, and I find that I need about 794. So now if I take that away from what I have remaining, I still have about 1,100 kilojoules left that I can now use to heat it towards its boiling. Now that we know how much energy is left over after we melt it all, we can see to what final temperature we can heat it. And so what we can do is we can take this amount of energy and see what kind of temperature change it would give. And if it generates a temperature change that puts us past our boiling point, then we know that our highest temperature will be our boiling point, or potentially beyond. And so what we can do is we can calculate our enthalpy change, and we just isolate for temperature change, and we put all of the energy remaining into that, and we see that we have a 600 degrees Celsius temperature change. And so this 600 degrees will keep us below its boiling point, so therefore we can calculate our final temperature.